Okay, this is going to be a video on friction test 2. It's the test you did last week, and I'm going to start off by going through some of the key concepts which a number of you are finding difficult. One of them is algebra, rearranging formulae, and the other one is interpreting the question and knowing which way to put the friction on the diagram, the friction force on the diagram. So we're not going to start off by doing question 1. We're going to look at some areas first. Question 3 will be done on a separate video, which I will call homework test stroke video. Okay, we're going to start by looking at rearranging formulae. I will show you an alternative method which some of you may find a bit easier when we come to do the questions. I will do the alternative method on 1B. Okay, and you'll see that it's very similar. We just use the calculator a little bit earlier to work out some approximate answers. A lot of you are finding it difficult to rearrange formulae when the variable that we're trying to write the formulae in terms of appears twice in the equation. So for instance, in this example here, if I want to rearrange this in terms of A appears in two terms. On the left hand side we've got M lots of A, and on the right hand side we've got B lots of A. Now when you're rearranging formulae like this, you have to get the terms containing the unknown you want on one side and everything else on the other. So what I'm going to do first off is I'm going to take away BA from both sides. I'm going to show you what I'm doing here on the side there so you can follow what we're doing. So if I take BA from this side, I'm left with nothing. Well, I'm left with that X, but that BA, take away BA gives nothing here. And if I take away BA on this side, I get that. Okay. Now I'm going to take away MX from both sides, so I'm left with terms containing A only. So I'm just showing what I'm doing here. So I've got MA minus BA equals X minus MX. Now this is a step you're finding difficult. Now if M and B were numbers rather than unknowns, you would now just subtract those two coefficients, well, one coefficient from the other. But because they're unknowns, you're finding it difficult to do what to do. So what we do in this case is we factor out the A. So instead of having MA minus BA, we have M minus B lots of A equals X minus MX. And now if we divide through by the bracket, we're left with A, and we're left with the formula written in terms of A. Okay. So that's what we're going to have to be able to do. Well, that's one approach for solving the question 1, which we'll use when we go through the problem. But if you're finding it difficult rearranging formulae, then go onto YouTube, look up rearranging formulae. There'll be a rearranging formula video or set of videos soon once I get round to recording them, but there's bound to be some out there already. Or look at some of the other software tools that we've got, or come and see me, because rearranging formulae is a key skill which we learn in GCSE, which we need to use at A-level. Now the next problem is identifying from the question which direction that the friction is acting in, which direction you have to put the frictional force on your diagram. Now when we first looked at friction, we had examples like this. We had on a flat surface, we had a particle which was being pulled with a force or pushed with a force F, and we always showed frictional force opposing that pulling force. And when it's a horizontal surface, if there's only forces being applied in that direction, the motion's going to be in that direction, which means the frictional force will oppose the motion. And that's the important bit. Friction always opposes motion. It would be wrong in this case, if there was no friction there, just imagine that's not there, to say, well, the friction acts in the same direction as the force. Okay, that's not possible. So the friction always opposes motion. So you're really quite comfortable when you first start off doing problems like this, putting the friction opposing the force which you think is moving the particle. Now the issue we get though is when we start putting things on slopes like this, and again there's a particle with weight acting down and normal contact force acting perpendicular to the surface. Now if I put a force up in that direction, you instinctively say, well, when we have the horizontal case, the friction's always opposing that force acting up the slope. But now we've also got another force acting on this particle. We've got the component of this weight acting down the slope. Now that means we've got two cases. We've got the case where this particle is about to slide up the slope, or we've got the case where the particle is about to slide down the slope. And that depends on the balance between this force here and the component of the weight acting down the slope. Now when the particle is moving up the slope, or about to move up the slope, and you'll see that in the question, the frictional force is opposing motion. So it'd be quite right to put the frictional force in that direction. Now in the other case though, when the particle is about to slide down the slope, because the component of the force, of the weight, acting down the slope is greater than the force acting up, or just greater, so it's just about to slide down, that means the frictional force is opposing that motion. So this is about to slide down, and this is about to slide up. And you really need to look into the question to think about it. And remember, the frictional force always opposes motion. So if they're telling you it's about to slide up the slope, then the frictional force will be down. And if they say it's about to slide down a slope, then the frictional force is up. And that's very important that you get those two aspects right. Otherwise, every model you set up will be incorrect. And a lot of you got the maths perfectly right, but you got the initial model wrong. You were answering part B in part A. And then when you came to do part B, you didn't know what to do because you'd already answered it. So you just tried to do something else. You weren't quite sure what was going on. And then you lost lots of marks, which resulted in disappointing marks. Those who did start also struggled on rearranging formulae. So that's our aside. And what we're going to do now is we're going to actually look at the question 1. So there's the question, and you should have a copy of this question at home anyway. But a sack of weight 600 newtons, so be careful. They haven't given you a mass this time, they've given you a weight, so be careful of that. Is being loaded on a track up a ramp inclined at 18 degrees to the horizontal. A rope attached to the sack is held at an angle of 25 degrees to the ramp. And you all seem to get that bit right. That was brilliant, so you didn't have a problem with that bit. The coefficient of friction between the sack and the ramp is 0.3, so that we know that we have to add a frictional force, and we need to find the tension in the rope for A, to prevent the sack from sliding down the ramp, and B, to pull the sack up the ramp. So there's two cases here, and what they're testing is, or what they're trying to show you in this question as well, what they're trying to teach you via this question, is that depending on the direction of the frictional force, the tension will be quite different. Okay, now in both cases we're going to take the acceleration to be 0, because in the first case it's about to slide down the ramp, and in the second case it's travelling at a steady speed, so there's no acceleration. So actually the mathematics on the model just has a friction in a different direction, and then the workings are identical. So I'm going to show you two alternative methods depending on your skills in rearranging formulae. You might prefer the second method, which I'll show you on part A. But as normal, the best thing you can do is work through these questions yourself with me. So I would like you to start by drawing me a good diagram of the situation. So here's my diagram. Well, it's missing one force, as you'll see. Actually, it's missing the frictional force, but it's nice and big. It's nice, and you can see the angles on there. I've added the angle in here, which is always worth adding, because we'll need that later on. I've only put real forces on there. I haven't put resolved forces. And I know when I said in my last video I don't like you to put resolved forces. I don't mind if you only put resolved forces. What I don't want is both of them on there. So you either choose to put the real forces only or the resolved forces only. Okay, so I don't mind which, but I will always show you real forces only. Now, we've got to put a frictional force on here because there's a coefficient of friction of 0.3. We also know that the acceleration up the slope is equal to 0, and the acceleration perpendicular slope is equal to 0. So we look again carefully at the question. It says to prevent the sack from sliding down the ramp. So the sack is about to slide down the ramp. Okay, about to slide down the ramp. So we've got to think what tension in this cable will prevent this sack from sliding down the ramp. Well, if it's going to slide down the ramp, we've also got a frictional force acting up the ramp. So that's my complete diagram. So in this case, the frictional force is acting up to oppose the motion down. Because in combination with the frictional force will help support the particle in place. So we don't need as much tension in the cable as we would have needed if that was frictionless. So now I've got a good model. I'm going to resolve. So I'm going to resolve. It doesn't matter which direction I resolve first, but I'm going to resolve perpendicular first. I'm going to use F equals ma, and going to take the direction of out of the slope as positive. Okay, so I'd like you to now do that and see what you get when you resolve it. So pause the video. Right, so the forces acting out of the slope are going to be the whole of r plus t sine 25, so it's the component of that tension out of the slope. So they're the two positive forces acting, and the negative force acting, because we're taking out that way to be positive, so this way is going to be negative, is the component of that force acting in line with that r. It's going to be minus 600 cos 18, and that's going to equal 0 because the acceleration in this here, the Newton's second law here, is 0. So now we can say that r equals cos 600 cos of 18 take away t sine of 25. So that's our resolved direction perpendicular. So hopefully you got the same thing. Now can you resolve parallel taking up the slope to be positive? Pause your video. Okay, I've zoomed out a little bit so that you can see the diagram, but hopefully you can still see the text. So now we're going parallel with the slope, so the forces acting up the slope are positive, and that's going to be the whole of friction plus t cos 25. And if you're getting the resolving forces wrong, come and see me very quickly, because that's something you've got to crack very quickly. And then 600 sine of 18, and that's going to equal 0 again. So now we can say that the frictional force equals 600 sine 18 minus t cos of 25. Now when we look at those two equations, 1 and 2, we've got three unknowns. We've got t, r and fr that we don't know. But there's a third equation that we can use to help us solve what effectively is a simultaneous equation. And that is the link between frictional force and the coefficient of friction and the normal contact force. So when it's about to move, frictional force, when the particle is about to move, in this case a sac, is equal to the limiting of friction, which is equal to mu times by r. So that frictional force there is equal to mu times by this r here. So I can write that as 0.3 lots of 600 cos 18 minus t sine 25. So that frictional force is the same as this frictional force, so now we can write 0.3 600 cos 18 minus t sine 25 equals 600 sine 18 minus t cos of 25. Okay, and at that point we've got to multiply out as much as we can and then rearrange. Okay. I'm going to go through it quite slowly. So first we're going to multiply this bracket out. So we've got to find 0.3 lots of 600. 0.3 times by 600 equals 180. So that's 180 cos 18 minus 0.3 lots of t sine 25 equals 600 sine 18 minus t cos 25. Now I'm going to add t cos 25 to both sides so that I get t's on the left hand side. So t cos 25 plus 180 cos 18 minus 0.3 t sine 25 equals 600 sine 18. Now I'm going to take away this 180 cos 18 so that I'm left with just terms with the unknown t in on the left hand side. So I get t cos 25 minus 0.3 t sine 25 equals 600 sine 18 minus 180 cos 18. Okay. Now factor out the t and we get cos 25 minus 0.3 lots of sine 25 all times by t equals 600 sine 18 minus 180 cos 18. And our last step then is to divide through by the bracket. T equals 600 sine 18 minus 180 cos 18 all divided by cos 25 minus 0.3 sine 25. And then you carefully put that into your calculator and you give your answer to 3 significant figures. So try typing that into your calculator now and let's hope you get the same answer. Now I get 18.2 newtons to 3 significant figures. Now there's a lot of rearranging formulae here and a lot of people say, well, that's actually not needed. Don't need to do it that way, you can do it another way, and that's overcomplicating it. And I do agree to a certain extent, and to be honest with you, that's not the way that we would have done it when I was at school. The reason why I wouldn't have done it like this when I was at school is because I didn't have the scientific calculators like you do. Now I will say though, if you keep putting the question in here and getting the wrong answer, just check your calculator set on degrees. Okay, particularly now that if you start working with radians as well. There should be a D in the display, not an R. And if it is in radians, then change it to degrees. So that's not the way I would have done it, and I'll show you how I was taught how to do it in part B. And just because we didn't have the same level of calculators. If you can do it that way, then you keep you don't do any rounding until the very last step, which is got arguably the better method. But if you're finding that just too complicated at this stage, then, as I said, look at the second part. Okay, so question 1 part B, and again I'm going to show you a slightly alternative method for dealing with the computation at the end. Now, whenever you start a new part of a question, don't use the previous diagram. Draw a new diagram. It will prevent confusion. So try and draw a diagram for the second part. So the details are exactly the same, but in this case we've got to find the tension needed to pull the sack up the ramp at a steady speed. So pause your video. So here's the diagram for part B. You'll notice that it's identical to the previous example, except the friction is acting down the slope as the particle is moving up the slope at a steady speed, and I've shown that again by acceleration equals 0. So two very similar problems, just one with the friction acting down and one with the friction acting up. So when you did part B for part A, you were then stuck for what to do for the second part, and you struggled and then lost a considerable number of marks because of that. So we're going to do exactly the same as before. Remember I told you, if in doubt, resolve. So we're going to resolve, and it doesn't matter which way you do. You can do the perpendicular direction first, or you can do the parallel direction. Everything acting out of the slope is positive, everything acting into the slope is negative, because that's how we've defined it in this diagram, and everything at a right angle perpendicular to that is 0. So we have the whole of r plus t cos 25 minus 600, apologies, that's not cos, that's sine 25, 600 cos 18 equals 0. Double check you're resolving. If you're not sure, just double check. Now I spotted that mistake quite quickly, luckily. Okay, so it's 600, that's t sine 25. So then that means that r equals 600 cos 18 minus t sine 25. Now this is what we're going to do differently compared to last time. Last time we kept the number as accurately as possible for as long as possible, but this time we're not. This time we're going to actually work out 600 lots of cos 18. Now the final answer is going to be given to 3 significant figures, so when we work that out we must work to at least 4, but preferably 5, so that we don't get rounding errors in our final example. So work out 600 cos 18 on your calculators. Remember, make sure it's in degree mode, and this is the way that I would have had to have done it. So 570.63. Now I'm going to put another one, because I just don't want to lose any accuracy. And sine of 25 is 0.4262t. Now, for some of you, that's nicer, particularly when we come to find t at the end. But if you can do the method A consistently well, then I prefer it. So now we're going to resolve parallel. So if you can resolve parallel and then pause the video, we're going to take up as positive, down as negative, and as usual a perpendicular is going to be 0. So once you have resolved, then restart the video. Okay, so everything acting up the slope. So if I zoom out a little bit, and we get t cos 25 is positive. Now this time the frictional force is opposing the motion. The motion is up, so the frictional force is down, so it's going to be minus Fr. The component of the weight is down the slope, minus 600 sine 18, and that's going to equal 0 because the acceleration is 0, so mass times by acceleration is also 0. So we can rearrange that now, and we get friction equals t cos 25 minus 600 sine 18. And we can work out those values. Okay, so that's frictional force. Now, in the previous example, we said that friction equals the limit of friction, which is equal to mu times by r, and it's exactly the same in this case as well. So this friction here is equal to 0.3 lots of this here. So we can write 0.3 lots of 570.633 minus 0.42262t is equal to that. And we can finish it from here. Now, it's very similar to what we did in part A, except we've now got numbers rather than the exact answers. So we've got simplified answers instead of the exact answers. So multiply out this bracket carefully, get everything containing t on one side, everything not containing t on the other, then sort the coefficients out. Now you'll be adding the coefficients this time, and you'll see why when you get there. And once you've got the coefficient of t, you can divide through. Okay, so see if you can finish it from here on your own. So first of all, I multiply 0.3 into the bracket, both terms, I have now added 185 to both sides, 185.4102 to both sides, and I've added this term to both sides to get this line. Again, that would have been the same as in the previous example, but why some of you will prefer it from here is you can actually add these two numbers together and add these two coefficients together, and without doing any factorizing. It's not the way I would do it anymore, it's the way I did it when I was at your age, but that was forced rather than by choice. So I would do it the way that I did in part A. Now you won't get any fewer marks doing it this way, or any more marks doing it the other way. It's a personal preference. So see if you can finish the answer from here. And this is the last few steps of the problem. These two coefficients added together to give that, so it's that lots of t. These two added terms together to give that, and then we divide through by the coefficient of t, and we get the tension is 345 newtons to three significant figures. And on to question 2 now. A car of mass 1,500 kilograms is making an emergency stop, leaves skid marks 7 meters long on the road. If the coefficient of friction between the tires and the road is 1.5, calculate how fast the car was travelling when the brakes were applied. Now this is one of those questions which actually requires a little bit of knowledge or general knowledge of what happens when someone pulls an emergency stop, and so there's a bit of required knowledge, and sometimes, I mean, if you don't drive you won't necessarily know what happens, which is why we say do as many questions as you can, because you also gain some experience at the time, and if you were stuck on this at home you could have come and asked me. So when a driver performs an emergency stop, he does two things. He presses the brake as hard as he can to engage as much force as possible, and secondly, he engages, or she engages, the clutch, so that the car is no longer being driven forward by the engine. When you put the clutch in, you take the power from the engine out of the gear system so that it doesn't drive the car forward. Now there's all sorts of technology nowadays to try and prevent skids, so this book was written before that, so let's just ignore that. So let's not get too technical here. Let's just assume that the brakes are jammed on and then they skid along the road, causing the skid mark. Now in that case we have an initial speed, we have an acceleration, which I am going to put in this direction. I could have put it in the other direction because I realise it's going to slow down, and it doesn't matter which direction you put it in, because as long as you use vectors then the mathematics will sort itself out. It has a weight of 1,500 kilograms, so it's got 1,500 g newtons, a weight, so it had a mass of 1,500 kilograms, so, and it's got a contact force. So prior to the emergency stop, you could have described this model as having a frictional force in this direction plus a driving force in this direction, and that's the engine driving the car along the road. But when you perform an emergency stop, you only have the braking force applied by stopping the wheels from turning, and then the friction between the wheel and the ground. So the frictional force is in that direction, opposing motion. So they're the only forces on that diagram. Now quite a few of you in the test also put a friction and a force in this direction because you thought the car was driving down the road, and that's an understandable mistake, particularly if you don't drive yet. So it's a bit frustrating when you get given a question which requires some general knowledge or some driving knowledge, but that's could happen to you in an exam, so better that you see that kind of question now than you see it for the first time when you're sitting your exam. So there's the diagram. We've got an acceleration in that direction, we've got a coefficient of friction of 1.5, and we know that after the brakes are applied we get a 7 meter skid, so we're going to end up with a V equaling 0. And the purpose of this question is to find the initial speed of that car, which I'm modelling as a particle as usual. Now you might want to start thinking about trying to do Suvat equations. Now if you try and find the deceleration or the acceleration, But the problem is you don't have the initial speed and you don't have the final velocity. You do have this 7 meters here though. So there might be something you can do. But I'd rather you think about it in terms of a force problem first. This acceleration, which will actually be a deceleration when we come to model it, it will be a negative value, is produced by this frictional force. There's no other forces opposing that car travelling down the road. So we can work out what the maximum A could be by resolving forces. So we're going to resolve parallel to the slope. I'm going to use F equals ma, and I'm going to take that direction as positive. And what I get is the negative frictional force is equal to 1,500 A. So frictional force is equal to minus 1,500 A. So that's where that negative A, so we do know it's a deceleration. Okay. Now it doesn't matter if you do it the other way around and you had the A going that direction as well and you had the direction resolved going that direction. The examiner will mark it appropriately and follow your workings. Now if we could work out the frictional force, the maximum frictional force between these tyres and a surface, then we could find the maximum acceleration, or in this case deceleration. And we can do that by finding the contact force and using friction equals flim equals mu r. So I'm going to resolve in the perpendicular direction, taking up to be positive, using F equals ma, and we get r minus 1,500 g equals 0, so r equals 1,500 g. Now a student the other day asked me, is r always the same as the weight? And I said no, and you know why that's not true. And he then persisted. He said, well, how can we quickly find r? And the only way that you can safely find r, it resolve parallel to the direction of r. Okay, that's the only way. Make sure that you take into account all the forces acting on the particle which have an effect. So don't look for shortcuts. In this case, r is the same as the weight, but it's not always the case. So now we can say that this frictional force is mu r equals minus 1,500 A. So we have 1.5 lots of 1,500 G equals minus 1,500 A. So A equals minus 1.5 G, which is, don't forget we use 9.8 in maths, for minus 14.7 meters per second minus 2. Now, on my diagram, I have the acceleration declared as going in that direction. So that negative is valid and it's proper, it should be there, and it's showing that it's actually a deceleration. If you've got your acceleration arrow acting in the opposite direction, then you will have a positive value there. So don't think it's wrong because you've got a negative there and just cross it out. It depends on how you've defined acceleration in your diagram. So we've got negative 14.7. So now we can work the SUVAT part of the problem. We've got s equals 7. Now we're going to work in that direction as positive. So we've got to be careful because this s is not distance, it's displacement. So it's gone 7 meters in that direction. So if we're going in this direction, that 7 is positive. U is what we're looking for. V equals 0. Now A negative. And that's the reason why I defined that way to be positive in my diagram, to avoid a mistake, and then we don't worry about t. And then selecting the correct SUVAT equation, you get v squared minus u squared equals 2as. So 0 squared minus u squared equals 2 lots of minus 14.7 times by 7. So minus u squared equals minus 205.8. So u squared equals 205.8. We haven't found u yet. We have to do that by square rooting the 205.8. And we get the initial speed of that particle, or that car, was 14.3 meters per second to the right, as defined on my diagram. So that was a hard test. Hard test because the first question relied on you getting the friction around the right way, and the second question relied on you understanding a little bit about what happens in a car when you perform an emergency stop. So again, as many questions as you can do, the better, because you gain experience. The third question, which I set for homework, will be to set. I'll show you how to do it on a separate video.